All right, welcome to the deep dive. Today we are diving into something that, sounds like pure science fiction, but it's actually a cornerstone of how we understand the universe now, gravitational waves.
It's amazing to think that for like over a century, these ripples in space-time, they were just this brilliant idea from Einstein's mind, right?
Yeah,
And now they're real. We can actually detect them. And you know what? They're giving us a completely new way to see the cosmos.
yeah. A whole new sense to perceive the cosmos, as if we only had, sight before and now we have hearing.
Exactly.
Exactly. It's really cool.
It's incredible. So we've got a ton of material that digs into this. We're going to explore, what these waves actually are. Think of it like a cosmic echo, right?
Yeah.
And then we'll look at how scientists figure out how to detect something so faint, so small, it's unbelievable.
Yeah.
And most importantly, we'll discuss why this whole field of study is just revolutionizing our understanding of the universe.
It really is. I mean, think about it this way. For hundreds of years, we've been looking at the universe primarily through light. You know what I mean?
Yeah.
What scientists call electromagnetic radiation. Every telescope,
Right.
from the simplest to the most advanced ones like James Webb, it's all built to catch these photons. But gravitational waves, man, they offer a completely different way to experience the cosmos.
It's a whole other dimension,
It's
yeah.
almost like you've suddenly gained the ability to, hear the universe's most dramatic events. So our mission in this deep dive is to cut through all that complex jargon, get right to the heart of what makes gravitational wave astronomy so significant
Yeah.
and frankly, just mind-blowingly cool.
Absolutely. And I think, to get started, we should really unpack this idea of ripples in space-time. Because, I mean, it sounds like something straight out of, Star Trek or something.
Yeah, it sounds crazy.
Right. But it's actually a direct consequence of Einstein's theory of general relativity. So instead of picturing gravity as this force that pulls things together, Einstein showed us that massive objects actually warp the fabric of space and time around them.
They warp it. Okay.
They warp it, yeah. And then when these really, really massive objects accelerate, we're talking about, events on a cosmic scale here, that warping doesn't just stay put. It creates these ripples that spread outwards, just like, when you throw a pebble into a pond.
Right.
Those ripples, those are gravitational waves, and they travel across the universe.
So if I'm understanding this correctly, it's not like these waves are traveling through space-time. It's that they're distortions of space-time itself.
That's exactly right.
So they're stretching and squeezing everything in their path as they go.
Yeah.
And these distortions, they travel at the fastest speed there is.
Yeah.
Speed of light. It's a lot to wrap your head around. Now, you mentioned the acceleration of massive objects. What kind of cosmic events are we talking about here? What's powerful enough to generate these, space-time tsunamis, right?
That's a great question. And the things that cause this, they're as extreme as you can possibly imagine.
Oh, wow.
So one of the main sources that we've actually observed are these things called binary black hole mergers.
Okay.
So picture this. You've got two incredibly dense black holes locked in this cosmic dance, right?
Yeah.
They orbit each other, getting closer and closer. And as they spiral inwards, they finally collide in this just cataclysmic embrace.
Wow.
The amount of energy released is just unbelievable. And a lot of it is in the form of these gravitational waves.
Wow.
And the really cool thing is that the very first direct detection of gravitational waves came from an event just like this. It's called GW150914, billions of light years away.
GW150914.
Got it. And these waves, they carry information about the black holes themselves. We can tell, how massive they were, how fast they were spinning. We can learn about the dynamics of their final moments together. It's pretty amazing.
So binary black hole mergers, you've got these incredibly dense objects crashing into each other, like cosmic demolition on a grand scale. Are there other events in the universe that are shaking up the space-time stage enough for us to detect these waves?
Yeah, definitely. Another major source, and one that's really insightful, is when neutron stars collide.
Neutron stars. Okay.
So these are the ultra-dense leftovers of stars that weren't quite massive enough to become black holes. And when two of them merge, the gravitational waves they produce are often accompanied by a whole bunch of electromagnetic radiation. That's light across the spectrum, gamma rays, X-rays, the whole shebang.
Wow.
This is where multi-messenger astronomy really shines, right?
Multi-messenger. I
Now-
like it.
Yeah, you get to study these crazy events using multiple types of signals. It gives you a way more complete picture than you could ever get from just one type of observation.
It's like, using all your senses to
Right.
experience something.
Right. Right. So it's not just about hearing the universe through these gravitational waves then. In some cases, we're getting like the full cosmic sensory experience, right?
Exactly.
That sounds incredibly powerful. And the material also mentions supernova explosions, those big star deaths, right?
Right.
Do those also create these gravitational waves that we can detect?
They do, but the waves from supernovae are usually weaker and harder to detect compared to those from black holes or neutron stars merging. The key factor here is that the collapse of the star's core has to be asymmetrical.
Asymmetrical, okay.
Yeah, so if it's perfectly spherical and uniform, the gravitational waves kind of cancel each other out.
Huh.
It's the unevenness, the lopsidedness of the star's death throes that actually creates ripples in space-time that we can pick up on.
Interesting. So even in something as violent as a supernova, it needs a certain degree of, like, imperfection to really make waves, literally.
Right. Now, there's also something called primordial gravitational waves from the very early universe. That sounds like we're going way, way back in time.
We are. We're talking about going back to the very beginning, to the Big Bang.
Wow.
There's this theory called cosmic inflation, which describes this period of incredibly rapid expansion right after the Big Bang, like in the first fraction of a second.
Wow.
And the theory suggests that this expansion itself would have generated its own background of gravitational waves.
Interesting.
Now, if we could detect these primordial gravitational waves, it would be like looking directly at the birth of the universe.
Wow.
It could provide evidence for this theory of inflation and give us clues about how everything began.
That's huge.
It is. Unfortunately, these waves are incredibly faint, and while scientists are searching for them, they haven't been directly detected yet.
Okay, so we've got these incredibly powerful events creating ripples in space-time that travel billions of light years to reach us. But how in the world do we actually detect them? I mean, these waves are stretching and squeezing space itself, but it's on a scale that's just mind-bogglingly small, right?
You're absolutely right. The changes are so tiny, it's almost impossible to comprehend. Like, we're talking about changes on the order of 1,000th of the diameter of a single proton.
That is so small.
It's ridiculously small.
Yeah.
So to detect these minute changes, scientists use these amazingly precise instruments that use a technique called laser interferometry.
Laser interferometry. So can you break that down for me a little? How does that work?
Sure, imagine a giant L-shaped detector.
Okay, an L. Got it.
Each arm of the L is super long, several kilometers. At the corner where the two arms meet, they shoot a laser beam and split it in two. So now you've got two identical beams.
Okay.
And each of these beams travels down one of the arms of the L, bounces off a mirror at the far end, and then travels back to the starting point.
Yep.
And when those two light beams meet again, they create an interference pattern.
Interference pattern. Okay.
Yeah, think of it like those alternating bright and dark lines you see when, like, two waves overlap. You know what I mean?
Right.
It depends on whether the light waves are in sync with each other or not.
Gotcha. So what happens to this interference pattern when a gravitational wave passes through the detector?
So when a gravitational wave comes through, it stretches one arm of this L-shaped detector just a tiny bit, and at the same time, it squeezes the other arm. And then it does the opposite as the wave goes through.
Wow.
So it's like this tiny change in the length of the arms. We're talking about that subatomic scale we mentioned before, right? And that tiny change causes a corresponding shift in the interference pattern when the laser beams meet back up again.
Wow.
And it's an incredibly sensitive measurement, so it lets us indirectly see these ripples in space-time as they pass by.
So you're saying these massive kilometer-long detectors are looking for the tiniest flicker in a pattern of light. A flicker caused by a ripple in space that's smaller than an atom. That's pretty incredible. And, the sources really point to GW150914 back in 2015 as this huge moment for the field. Why was that first detection so important?
Well, GW150914 was a big deal because it was the very first direct detection of a gravitational wave.
Wow.
That confirmed a major prediction of Einstein's theory of general relativity, which had been untested for like 100 years.
100 years. Wow.
Yeah, it was really cool. And the signal we detected, it matched perfectly with what we'd expect to see from two black holes merging. One was about 29 times the mass of our sun, the other about 36 times the mass of our sun, and they were 1.3 billion light years away.
That's incredible.
Yeah, so it not only validated Einstein's theory, but it also launched gravitational wave astronomy as a brand new way to study the universe.
That's mind-blowing. I mean, to detect a signal from something that happened over 1 billion years ago, confirm a prediction made a century before, using technology that can measure changes smaller than a proton, It's just incredible. It makes you feel kind of small, but also just awestruck by the universe, you know?
Totally.
But why should our listener, you listening right now, care about all this? Like, what does this mean for you? What are the big implications of gravitational wave astronomy?
That's a great question. There are several. For one, it lets us test Einstein's theory of general relativity in really extreme environments. Like, we're talking about places where gravity is super intense, like near black holes and neutron stars. This is where we might find cracks in Einstein's theory, places where it might not work perfectly. And if we see that, it could point us to new physics, new ideas about how gravity works.
So it's not just about confirming Einstein was right, but also potentially finding the limits of his theory.
Exactly.
That's pretty cool. What else?
Another cool thing is that it helps us understand extreme matter.
Extreme matter. Okay.
Yeah, so when neutron stars collide, it's like this cosmic lab where we can study matter that's way denser than anything we could ever create on Earth.
Oh, wow.
By looking at the gravitational waves and the light from these collisions, scientists can learn about how matter behaves under these crazy conditions.
Wow.
It's like a window into the fundamental nature of matter itself.
That is mind-blowing.
Yeah.
And you mentioned multi-messenger astronomy earlier. Can you talk a bit more about why observing the universe in this way is such a game changer?
Definitely. So when we can detect both gravitational waves and light from the same event, like a neutron star merger, we get a much richer picture of what happened.
Right.
For example, the first binary neutron star merger that we detected, it's called GW1708-117. We were able to hear the collision through gravitational waves, but we also saw it with telescopes. We saw this bright radioactive afterglow called a kilonova. And from that one event, we learned a lot about where heavy elements in the universe come from, like gold and platinum. Yep. We also learned about gamma ray bursts and how matter behaves when it's moving close to the speed of light. It's like going from black and white to color TV. You get so much more information.
It's like upgrading all of your senses at once. So amazing. And finally, what about peering into the early universe using gravitational waves? How does that work?
So this is where the future gets really interesting. We're building space-based detectors, like the LISA mission, which will be much bigger than our current detectors on Earth.
Wow.
LISA will be able to detect gravitational waves from events that are too faint for us to see now, like mergers of supermassive black holes at the centers of galaxies.
Wow.
And maybe, just maybe, we might even be able to detect those primordial gravitational waves from the Big Bang itself.
Wow. That's just incredible.
If we can do that, it would be like looking back to the very beginning of time.
Wow. So from the echoes of the Big Bang to the collisions of black holes billions of light years away, gravitational waves are really opening up a whole new era of cosmic exploration.
Yeah, it's pretty amazing.
It's just crazy to think that these tiny ripples in space-time, something Einstein had predicted with pen and paper over 100 years ago, are letting us hear the universe in a way we never thought possible.
It's mind-blowing. It's a revolution in astronomy, and it's giving us a new sense with which to observe the universe, to see some of the most extreme events, and test some of our most fundamental ideas about physics.
It's a testament to human ingenuity.
It really is.
So as we wrap up this deep dive into gravitational waves, here's something to think about. We can now hear the universe, sense the warping of space-time from events billions of light years away. That's fundamentally changing how we understand our cosmic origins, the very laws of reality. What other secrets might the universe be whispering to us through these waves? What discoveries are waiting for us? It's an exciting time to be alive and witness this new era of astronomy.
Absolutely.
Thanks for listening to The Deep Dive.
Thanks for having me.